Hi, okay. So obviously there's a lot of confusion on the third CMOS problem. And so I'm just gonna go through quickly like kind of the approach as to how to stop the how to get there, because I think I assumed a few more steps than were actually like known. So we're gonna go back to this page of like PMOS and NMOS in different um like situations and see like how that relates to the output where we take it. So I rephrase the question. So like for each diagram, we're going to show when does V out equal V, where V is this like input source over here. And when does it equal 0, also known as like the ground. And so we're just going to go through and kind of like make a table for each one of them. So we're going to start with this one. So this is two PMOS transistors in parallel with each other. And we're taking the output like over here, which is after the transistors. So we're gonna make a table over here, and it's gonna be our source A, source B. These are sources directly to the transistors. So like, because remember how that VGS determines whether or not it's like how the transistor acts. So in this case, we're just saying if the if the sources are on or off, and then how that affects V out. So if A is off, so there's no voltage coming from A, and there's no voltage coming from B, then because it's a PMOS, that means that our PMOS is on, and that means that we're going to have a short circuit here and a short circuit here. So this means that current is flowing through both, I don't know what the word is called. Current is flowing through this portion of the circuit. So at V out, the voltage you measure is going to be the same as V. And so we're going to represent that with a 1. Okay, so then if we erase that, and we're going to say, okay, so now if A is, like there is voltage coming from A, enough for a logical on, and there's no voltage coming from B, so that means because it's a PMOS, your voltage on means that this is going to be an open circuit because your PMOS is off, and your B on the B side, you're still going to be on. So this is going to be a short circuit. So you still have current flowing through this side. So your circuit is still complete in this regard. So at V out, you're still going to measure V. So V out is going to be 1. So then we keep going through this, and it's going to, so now we're going to try A is 0 and B is 1. And so you're just going to have the flip scenario. So now this is going to become a short open circuit, and this is going to become a short circuit. Your current is still able to flow through this side. So V out equals V, and you're going to have a 1 here. And then for the final trial, you're going to say A is on, B is on, which means that both of these are open circuits because your PMOS is going to be off if its source is on. And that means that like this V out is completely disconnected from this voltage source. So this V out is going to be 0. And so we're going to represent that with a 0. And so as you can see, like if you look at this as a truth table, this represents the NAND truth table. So this means that number 1 is how to represent NAND as PMOS. And so now we can go over here and we can kind of make the same diagram. So now we're looking at two NMOS in series with each other. And your V out is going to be here. We're going to assume that there's like some kind of voltage that it's coming to. And so you're going to go A, B, B out. So now again, if A is off and B is off, then both your NMOSs are going to be off, which means they're both going to be open circuits. So there is no connection to ground, so V out equals V, and so that's going to be represented by 1. Now, if you have this as 1, this is 0, sorry, I shouldn't have erased that part. Then since your A source is on, so your NMOS is on, so this is going to be a short circuit, and then this is going to be an open circuit. So your V out, although the circuit is like kind of broken over here, at the point where you measure V out, it's still equal to V. So you're going to put a 1 there as well. And so again, it's the same thing when you go 0, 1, because for NMOS, you take the V out before you get into this portion of the diagram. So you're going to have so A is off, so this is, sorry, A is off, so this is going to be an open circuit. This is going to be a short circuit. But again, at the point where you measure V out, it's still going to be equal to V. And then if A is on and B is on, well then, both your NMOSs are on. So this creates a whole short circuit. And now your V out is connected to ground. So you can say that, like, since V out is connected to the ground, it's going to be 0. And you can have like anything basically up here. Like you could have resistors, you could have capacitors, you could have another PMOS. But your V out would be measured to ground because there has to be the voltage drop. So yeah, so as you can see, this is identical to what we got in number 1. So now this is also a NAND gate, but represented as an NMOS. And so in order to create a CMOS NAND gate, all we're going to do is stack this on top of this. So you're going to put your PMOS, so you're going to have your voltage source. It's going to go into, I just can't draw. What? There we go. Okay. So your voltage source to the entire circuit, and then you're going to have your 2 PMOS in parallel connected to your 2 NMOS in series. I'm going to represent that like that. And your voltage out is represented over here. And then this is going to be A, this is going to be B, this is going to be A, and this is going to be B. And so now you have a CMOS NAND gate, and you can always, like, if you're still confused about like how it still stacking 2 NAND gates becomes a CMOS NAND gate, feel free to like go through the truth tables again in the bigger scenario. But the important thing here is that you have this V out, which represents the NAND of A and B. So now let's say you wanted to create an AND gate, a CMOS AND gate, right? So you have a NAND gate, and in order to get from NAND to AND, like all that is so AND is an inversion of NAND. So we're going to invert this output over here. And we already talked about how to do that, which is you have like another thing here. So this is your NMOS and this is your PMOS. And this is, so now your output is going to be your like transistor inputs in this, because this itself is the inverter. So all you did is you linked up the output from a NAND to determine to an inverter. And so now when you measure this output here, you have a NAND, and then you inverted those results. So your final output is going to be AND of A and B. So you guys can feel free to work through like this truth table. And basically what you'll come to find is that this represents an OR gate for NMOS, and this represents an OR gate for PMOS. And yeah, so then you put those again on top of each other, and then you invert the output. and then this will represent OR. So yeah, I hope that helps. Sorry that was a little confusing. And yeah.